This is Module 7 from our online Introduction to Tensors for Non-Mathematicians course or set of videos. It's titled Covariant and Contravariant Transformation Rules. And what does this mean? Well, we have discussed already the forward and backward transforms for covariant change of primal basis and how they may be applied to both components of a primal vector. However, we need to define a similar relationship for other tensor types, including the dual tensor, which we just introduced in the previous video. Now, in this module, we're going to learn that for rank 1 tensors at least, and that would include both primal and dual vectors, we can categorize any component as covariant or contravariant. We can use these classifications. Then, based on that classification, we will know, or we can deduce, how that component will respond to covariant change of primal basis. In short, this module serves as kind of a direct sequel to module number 5 that introduced the forward and backward transforms themselves. Using the primal vector as the example, we demonstrated how to apply those transforms to the primal vector. And so now what we're doing is expanding that to the dual vector. In a more broad sense, we're introducing the terminology, the language that will be required to extend that concept to higher rank tensors such as linear maps and bilinear forms. The highlight of this module, of this section, is the table on the final slide, which defines the appropriate transforms for all components of both primal and dual vectors in terms of their covariant and contravariant characteristics. As the course title suggests, these videos are aimed at those with an interest in science and engineering, as well as some background in linear algebra who want to learn more about tensors. I have written a text to accompany these lectures. A link to that text will be available in the description once it's available. Again, as I always say, I'm still working on that. If you have any questions, comments, any sorts of corrections, please place them in the comments. I will be checking them frequently, and I will make corrections myself whenever they're warranted. As always, please like and subscribe if you'd like to see us produce more STEM and engineering related educational videos. Let's discuss the contravariant and covariant transformation rules. Now, during the conclusion of the previous module, we gave a little bit of a preview of what this means. Essentially, we want to expand, to elaborate on the transformation rules that were defined as part of, I think, module number 5, where we demonstrated how to apply a transform to the primal basis set, and assuming that we apply that transformation, what corresponding transformation we need to apply to the primal coordinate array. So we're trying to elaborate upon that section here and discuss how we can apply appropriate transforms to primal vectors, dual vectors, linear maps, all the other types of tensors that we'll see moving forward. And a lot of this comes down to understanding what are covariant components that follow covariant rules, and what are contravariant components that follow contravariant rules. Now, we haven't really discussed those terms at length, but we are familiar with what they mean with respect to at least indices, right? If we have a matrix A, we can define the individual elements or identify them in terms of two different indices, right? We call the subscripts the covariant indices, and we call the superscript the contravariant index. Okay, or contravariant indices. Now, the bottom denotes the column that we're working with, or shows how we move throughout the matrix from right to left. The contravariant refers to the row, or shows how we move through the matrix top to bottom. Now, we'll see there is going to be some relationship between how we use these terms here and the overall more robust, broad definition of what's a covariant rule and a covariant component. So let's jump into what we have, what we want to highlight here. The covariant rule is defined by the transform of the primal basis as shown in green. Now, this equation should be nothing new. We know that the basis set post-transformation is equal to the basis set pre-transformation times some sort of forward transform matrix. And this is a fundamental definition of what the covariant rule is. The covariant rule is defined by the primal basis of, well, the primal basis set and how that set transforms. Anything that resembles it and reacts similarly to a change of basis will be represented or called a covariant component that follows a covariant rule. Anything that follows the opposite or has the opposite inverse relationship, we will call a contravariant component that follows a contravariant rule. So the previous table, the one from the previous module, demonstrates that this rule applies to both the primal basis set B as well as the dual covector coordinate array gamma. A component that obeys the covariant rule is referred to as a covariant component. So obviously, the primal basis set is a covariant component, and we just learned that the dual vector coordinate array will also be called a covariant component. If we stretch or compress the coordinate system for a given tensor, covariant components will scale in the same way. So I want to draw a table here for a second. This is similar to a table from one of the previous modules. And what I'm going to describe here is we have some characteristics of a primal vector, of a dual vector, how they apply to the coordinates as well as the basis. Now, we know already from the previous slide that by definition, the primal basis set is a covariant component. Okay, and we saw that because the dual vector coordinate array follows a similar transformation rule, it's also a covariant component. The primal vector coordinate array transforms in the opposite way. If you remember, right, we saw that B post is equal to B pre times F pre post. However, if we want to update the coordinate array, okay, that is going to be equal to B Okay, so what we're trying to show here is that the coordinates of the primal vector transform in the opposite way, right? Very specifically here, we're showing that this is the opposite transform to what is shown below. So the primal coordinate array will be referred to as a contravariant component, and the basis of the dual basis set will also be a contravariant component. Okay, and what we're going to see, although we haven't explicitly shown it yet, is that when we try to calculate the basis set, the dual basis set, we are going to use a rule that looks very similar to the coordinate transform from the primal vector. Okay, so we've talked about what a covariant rule is. The covariant rule is defined by the behavior of the primal basis transform, and any component that follows the covariant rule is referred to as a covariant component. Now, a contravariant component follows the contravariant rule, and it's essentially just the opposite, right? This is what I was trying to show here, is that the primal vector coordinates follow the contravariant rule simply because it is the opposite of how the covariant rule is applied to the basis. Now, not to go too much onto a sidetrack here, but yes, right, definitely the characteristics of the covariant and contravariant components, they're very closely related to how we apply change of basis transforms. And so that's one of the main ways that we can identify them, and one of the main reasons why we have to be familiar with the difference. Okay, so the contravariant rule is the inverse of the covariant rule. Really, all you have to know is that the covariant rule is defined in terms of how the primal bases are transformed, and anything that's contravariant does the opposite. In other words, you use B here instead of F, where B is the inverse of F. So a component that obeys the contravariant rule is referred to as a contravariant component. If we stretch or compress the coordinate system for a given tensor, the contravariant components scale in the inverse or opposite way. So what we see here is that contravariant components scale the opposite way from the tick marks along their axes, and the covariant components scale with that. Now this makes sense because if you think about a vector, right, as equal to some basis set times some coordinate array, it makes sense that these would scale in opposite ways, right? Because if we take B and we multiply that by 2, we would need V, the coordinate array, to divide by 2 in order to maintain the same vector, resultant vector value. And okay, that's what we're showing right here. Actually, I did the exact same thing. So if we imagine a vector projected to some axis, right? If we lengthen those axes, increase the distance between the unit length ticks, which is what we are doing here with the 2b, we're essentially, you can imagine what we're doing there is if we take this example axes where the length of these primal basis vectors is the unit length, and we extend it by 2, right? We get rid of that tick mark. We're essentially doubling the distance between the tick marks, where those tick marks represent the unit length for our entire space. So how do the covariant and contravariant rules relate to the covariant and contravariant ranks, as well as I'm going to throw in there the indices, because we're familiar with those. We talked about those previously. Covariant row-oriented arrays. What does this mean? Components that obey a covariant rule are generally represented as a row-oriented array and therefore employ a covariant index subscript. We know this, right? If we go back to our table here, we've seen that, okay, let's start off with the covariant components. We've seen that the basis of a primal vector, and I know I'm running out of space, is essentially a row, right? We have B1, we have B2, ... So this is a row-oriented array. Now, if we take a look at the coordinates of a primal vector, generally, right, that would be V1, V2, ... That would be a column-oriented array. So the covariant components will be indexed by covariant indices, and the contravariant components will be indexed by the contravariant indices. The covariant components will have a non-zero, will have at least one covariant rank, and the contravariant components will have at least one contravariant rank. And then we repeat the same sentence, essentially, but for contravariant components. So components that obey a contravariant rule are generally represented as a column-oriented array and therefore employ a contravariant index superscript. If you remember, when we talked about 3D matrices, I said that I didn't favor representing, a matrix with a third rank as this stacked set of matrices like a cube, and that's because this third dimension is neither vertical nor horizontal, so it can be difficult for us to determine whether that's an additional contravariant or covariant rank. And that's why we are going to opt for notation like this, where anytime we have an additional rank, we add that as an embedded row or column array. But we can see here very clearly, if it's a row-oriented array, that's an additional covariant rank. And if it were a column, then that would become a contravariant rank. So the covariant or contravariant nature of a tensor says a lot about its structure and behavior. Now moving forward, it's only really the primal and the covector or the dual vector that can be described, or its components can be described purely as covariant or contravariant. The next type of tensor we're going to talk about, which is the linear map, is a combination of contravariant and covariant components. So we can break down the coordinate matrix, break down the basis set into its individual covariant and contravariant components, but it's going to become increasingly difficult to separate them in that way. Still, that being said, these descriptors are one very important way of describing our tensors. Most importantly, when we describe the tensor in terms of its covariant and contravariant ranks. So here, this slide provides a table, and it says a lot. So let's take a second to look at it. Well, first off, it shows us all of the different transformation rules, both forward and backward, for the primal as well as the dual basis. So above here we have the primal, below here we have the dual. Okay, this would be the basis set, the coordinates, the basis set, the coordinates, b, v, beta, gamma. We say very clearly this employs a covariant rule, employs contravariant, employs contravariant, employs covariant. And then we can see the forward and backward transforms. Okay, so let's start off with the one that's the most fundamental, and that is the forward transform of the primal basis. B post is equal to B pre times the forward transform matrix. We expect to see a similar forward transform for the other covariant component, which is down here, the covector coordinate array. And we do. Gamma post is equal to gamma pre times a forward transform matrix. And that's what this orange arrow is showing. It's relating all the similar components. Okay, but for now, I'm going to put an A here and an A here to indicate that they behave similarly. Now, let's take a look at maybe the most fundamental contravariant component, which that would be the vector coordinate array. So V post is equal to the backwards transform matrix times the pre-transform value. We expect to see a similar type of behavior for the other component that employs a contravariant rule, and that's the dual basis set. We do see a similar form. Beta post is equal to that same, right? This is the same matrix, okay? And then this is also the same matrix. Okay, B post is equal to the backwards transform matrix times the pre-transform value. So A and A, right, they exhibit similar behavior. B and B, they exhibit similar behavior. And really the right-hand side of this table, all it's saying is obviously the backward will be the opposite of the forward. So wherever we have an A, it'll become a B. Wherever it's a B, it'll become an A, and so on. So if you follow this orange arrow, what you can do is you can see all the elements of this table that use a similar transform, and then you could follow the blue arrow in the same way. So this table is one that I do recommend you take a second to look at. It does clearly explain a couple of things. Well, first, how do you apply the forward and backward transforms to both the primal and the dual vector? Second, it also does a very good job of explaining the role that the term covariant and contravariant rule or component, what that classifier means with respect to these transforms that we're using here. This next module discusses the linear map, a tensor whose structure and behavior most closely resemble that of a traditional rectangular matrix, but with some information on basis or referential directions embedded within it. This is the first tensor type that we introduce with both covariant and contravariant ranks greater than 0, meaning that it has both height and width, whereas the covector represented a functional mapping between a primal vector and a scalar value. The linear map defines a relationship between two primal vectors, one being the input and one being the output. This more complex tensor also allows us to shed some of the assumptions associated with the less complex primal and dual vectors. It facilitates a more advanced look at how these tensors work in the broadest sense. A link to the next lecture is available in the description below, or will be available very soon. I look forward to reading your questions and potentially corrections in the comment section.